Welcome to the next session of Definition. So my name is Kräuter. So first time here at ICGT, and there will be 3 talks, and the talk is titled "Rutle procedure for graph variable solving," and talk will be given by Rachid and Echahed.
This talk is about the use of rewrite techniques to solve graph queries over graph databases. And this is joint work with Dominique and Frederic in Grenoble. So, as you may know, there is a shift going from relational databases to graph databases currently. In relational databases, data are stored as relations or tables, and queries go from tables to tables. Okay, and there's well-known isostandard language called SQL. As for graph databases, so data are stored as graphs, and queries go sometimes from graph to tables. For those who like to be faithful with SQL, and there's new kind of queries which go from graph to graphs, kind of graph summations. And there's no yet nice standard, but it's under progress and will be released by the end of this year or next year. However, there is a W3 standard called Sparkle, and there are many other languages proposed either by industry or researchers. So there's so many issues to investigate. So when we speak about graphs, we know here that we have to be precise which graphs are we using, or in what kind of properties on that graphs, and which kind of queries, and how to solve these queries, how to make verifications, how to have classes, etc. There's so many topics to investigate. So which graphs? So there are mainly 2 classes investigated. So this one is RDF graphs used in Sparkle. So these graphs are very, very simple. These are sets of triples. Triple could be seen as an H with its source and its target. So here I just scheduled a toy example where I picture the fact that there's a train between London, between St. Pancras and the station of Leicester, and this train can be on time or scheduled or cancelled. Then the line, which line is? What cancelled? Yeah, I was told, I received a mail that mine is cancelled, but it was scheduled but not on time. Anyways, however, what we can remark here is we can have ages between ages and node, or ages between ages. So just an agent which goes from itself to itself. It's a graph. Anyway, the other kind of graph are property graphs. There are several definitions of property graph which are not equivalent, but they are very close. But anyway, these kind of graphs are kind of Baroque style, where nodes and ages are over decorated. So I put the same information. So we have a station here in London called St. Pancras, and was built in this year, and the other one in Leicester. And here we have the information about the train. Here the line, the number of the train, it's a variable. I don't know which were the train, and in the case of RDF, they don't speak about variables but about blanks, but these are variables. And here you have this red things, kind of typing information called labels in property graphs. Anyway, we know that in the graph transformation community, very often results are stated regardless the definition of graphs, provided that we can do, add, remove, etc. It depends on the category. And in this work, despite we try to be algorithmic, we try to be as generic as possible. Okay. So what about queries? So as I said before, there are two kinds of queries. So the select queries are also called match queries in Jekyll. In this kind of queries, one can give a graph. I'm simplifying things. So here we are looking for students X that are supervised by a member of a lab Y. And we are looking, for instance, for the students in the lab. Okay. With that, I give here a condition as a graph saying that students supervised by someone T who is a member of a lab Y. And we can here find two matches, the first one here and second one here. And so the first thing we have to notice is we have to compute a set of matches, okay? And then we can get the right answer here. So David is in lab 1 and Eva in lab 2, okay? This is the classical word of SQL in relational databases, even if this table could be seen as a graph. In the other kind of queries called constant queries. So I here give the same condition, okay? But instead of just displaying X and Y, can construct, this is a graph, could be a huge graph, saying that I add this age, linking student with its lab and get this kind of new graph, okay? And semantically, the outcome of this query would be this graph consisting of these two ages with their source and target. So in this work, we focus on sound and complete procedure to solve this kind of queries. And for that, we had to define clearly the notion of queries and nested queries. And it happens that the queries, as I introduced them, are not easy to nest. So we first define the notion of patterns, which are the main structure. This could be seen as a formula in graph logic, in dynamic graph logic. And to define precisely the semantics, we have to provide some operations over graphs. So the graph could be algebra. So I will start with this kind of algebra. So I give you the signature. So we need sort of graph. So we have, for any association, we have to say which kind of graphs we have, the carrier of the graphs. Some means that set of matches. So we'll manipulate a set of matches, and these can be defined directly from the graph here. So these are sets of graph homomorphisms. Expressions, could be any expression you can imagine in databases. And what is very important here is the use of aggregation operations. So these operations are not easy to handle. So you have some care should be done when we are manipulating aggregations, and var is will be interpreted by a set of variables. Okay, then you can define a set of operators. For instance, here we have the match operator. So here I give you idea about some of these operations. So match graph L and G is a set of all matches from L to G, and the join of two set of homomorphisms is a set of homomorphisms which are which coincide on in the intersection. So if this one goes from L to G and this for R to H. So I'm given definition in this in the case of RDF category RDF graphs. So we have here L union R into G union H, and each time M and P should be compatible. So what is interesting here are these two, bind and build. So bind have three parameters: a set of matches, an expression which may include aggregations, and a variable. And the role of this operation is to add a new node named X and evaluate expression E using this set of matches, and for each match construct a new node here if not yet present in G. And the build filter is just kind of concept. You are innating some useless homomorphisms, and the build take a set of homomorphism and a graph and construct the image of this graph using all matches in M. Okay, so it's the definitions. Now, this set of operations you can define as far as you want, according to the kind of queries you want to do. So, as I said before, so patterns are more meaningful for us here. And the pattern could be seen as formulas. So we have this empty close or empty pattern. Any graph is a pattern. So we add this constructor, basic of L, and a pattern can make a join with two patterns, and the bind and filter and build. So the semantics of the empty pattern is the empty set of homomorphisms going from empty graph to G. So this is the empty set, and the semantics of a graph, or basic of a graph, is with respect to a graph G, is all the matches going from L to G. Okay, so we can go like this. So what one remark here is when we consider this pattern, first we have to evaluate the pattern P1 on G, but since patterns can have this bind and build operators, so G can evolve, can be modified. So the evaluation of the second one should be done over this graph augmented, but with the effects of the first one. So the bind is, do what it should do. I mean, since we use the bind operator in the algebra. Okay. So the filter is evaluating E if it is positive, if it is true or not, and eliminate them. And the build it's add to the evaluation of the graph, the original graph, and add are associated with all the matches. Okay, so there's some examples. So in the first two examples of queries, I give this example saying that student supervised by variable T, person T member of Y. So this is a graph. So basically this graph is a pattern. So the one used in the construct query was this one, this pattern P, build this this graph. Now, if you consider this graph here, this pattern, it plays a kind of let expression in functional programming. It means that this pattern will add new relation or new edges to the considered graph, and P4 will use this edges. P4 says that if I have a student which is entering in lab 1, then I have to say that this student should be funded by grant this number. Okay? You can get this one. So the first P2 added this red arrows, and the second P4, this pattern, used this arrows and add this green one. Okay.
So where do you see here the start graph you start with in this expression?
I didn't write it. I have to, for the semantics, I have to say this P4, P2 join P4 over G. Okay. So now back to the notion of queries. So we have these construct queries. General shape is construct a graph where a condition is a pattern. Okay. So we translate this query to this into this pattern, saying P build R, and the result of the construct, okay, is the image of R, okay, just a projection of R using the different matches that we compute by P. As for select queries, so we have select S where P, so we evaluate P first on a graph, and then S is a set of variables. And since these are sets of homomorphisms, so we have just to take to make a projection on the set, the values of the variables. Okay. So now, how to solve a pattern? In general, if you see the pattern P as a formula in mathematical theory proving, we have a goal, you have inference rules, and then you make some inferences. You can make a derivation. It should be an empty clause or so a final goal. And then you can get a solution by making the composition of the substitutions. Here, we are not dealing with single substitutions. If we deal with single substitutions, we can have inconsistent solutions, and it will not be sound. However, we will compute sets of substitutions, of solutions. And we will start with the initial pattern and transform it by some rewrite rules until the empty pattern with set of solutions. And here we will get the final set of solution of a pattern. This is the idea. And these are obtained by a set of rewrite rules. So I can explain more or less how it works on 2-3. For instance, so we define a solve operation which takes a pattern and a set of solutions and say how it behaves. Here, for basic L, if you have just L, and we know that the graph under consideration is G, so we consider all the matches from L and G and put it as a result here and erase this one. Okay. So here, this is not a direct transformation, since we are looking for matches here, and L may contain variables, and here variables are unassociated. For the solve of this pattern, P1 join P2, it happens that join here is not commutative because of the side effects of this, the bind and the build. So we start with the left to solve this, the left pattern. Okay, you can say that solve P1 with the current solutions, and P2 is memorized, and solve this join left assumes that if this one is solved, the normal form is of this form, so it should be the empty pattern and the set of solutions. And in this case, we will have this argument here, and go and solve this the right pattern with this this function solved join right. And once this one is solved, goes to the normal form with the empty pattern with a set of solutions M prime, then we can get this normal form where P is a joint is as defined in the first algebra of M and M prime. Okay, so and the rest is of this kind. So to solve a pattern P over a graph G, we should start with this configuration of this term, where IG is a kind of identity for a classical alternative proving, but here it's the singleton of morphism going from the empty graph to this graph. Okay, and we try to use the set of rules until this normal form. And once the normal form is obtained, this the variable M is a set of solutions of the patterns. So we can prove that that this transformations always terminates, and it is deterministic in the sense that even if P can be listed them as big as we wish, there's only at each step there's only one redex, and all solutions are sound, and any solution can think of can be computed. So these patterns are very close to graph formulas. So nested graph conditions are close to what we did, but there is no aggregation operations in them, and they do not consider graph modifications. And the classical nested graph conditions express conditions on the shape of graphs, and in order to go further on, to express conditions on shapes, on attributes, there are some extensions, for example, this one. As for graph database language theory, there are a lot of nice work with clear semantics, but they all, very often they consider variable assignments as semantics and not set of graph homomorphisms, which prevent from doing this kind of nesting. Okay. In summary, so we defined a class of nested patterns. This pattern could be extended if we, as far as we want. For instance, here we didn't consider, for instance, path, so we can add other operations about paths, but it will take 3 or 4 pages more. We give some complete rule-based calculus. Calculus is generic in the sense that it can be adapted easily to any notion of graph. We have just to define the interpretation of the graph query algebra, and the proof data can be defined in our archive report. I just have one ad. So we're hiring a postdoc to 1 year postdocs if you know someone on these subjects and working directly or with people working on Jekyll language. And so the future work include verification techniques for graph databases, and this is one of the motivation of this work. So before thinking about verification techniques, we have to have a clear definition of what we are doing. We are revisiting this work in the light of a first algebraic approach appeared in GCM 2020. Of course, we wish to cope with the forthcoming Jekyll language and implementation of the proposed calculus. Thank you very much.
Questions? Remember the examples of graph databases. One was in Grenoble, something like 20 years ago, or 25 years ago, you might remember the name. The other one was in Zurich. And the third one I remember was in the R group, which was for graphs. But these had a completely different interface. So your interface, you have very high level, very aspect that was graph oriented in the sense you start at a certain node, you can walk by a certain path and another path, and trying to find nodes being reachable for both, having certain attributes and so on. So can you relate your approach to the other approaches on one hand, and can you tell something about the implementation?
Not aware of kind of work you said.
There was a European project in shows it non-standard database systems.
Okay.
As far as I remember, one was in Grenoble, and the other ones were elsewhere, because all of them are driven by that usual database systems are not suitable for these kind of applications. They are for mass data and for tabular data. Now we need different things.
It's difficult for me to answer if I don't know exactly what it's about. So this is a theoretical work. If we have to handle big data, for instance, I don't know if you are thinking about huge database, one has to think about how to implement this matching action. When I said match LG, I mean it's easy to say, to write, but to implement, I mean it's very complicated if we consider a very, very huge database. So I have no idea about how to do such kind of things. Okay.
I would mention graph databases are actually much older than that. Graph databases are actually older than relational databases. They came about in the 1960s. And I guess to some extent, relational databases won out because of Holt's algebraic model of them. So it's good to see an algebraic model of graph databases. Somewhat late.
Just a question on the set of rules.
Yeah.
It's very similar to the approach to define the simplification algorithms by simplification.
Yes. So was inspired by narrowing techniques.
Yeah. But this particular presentation of the algorithm as simplifications. What I was wondering is why you choose a presentation that is deterministic rather than often you see these ones as non-deterministic. You simplify.
Okay, it's better to be deterministic.
So I was wondering, obviously you don't need to prove confluence because you have only one.
Yeah, but the problem is if we can so the first intuitive rules will say that join is commutative, but in fact it is not. So if we, so this kind of context-free grammars which are ambiguous. So we can implement the ambiguous one. And the ambiguous one, it's not sound at all, because here it instead say, I start with solve the first one. I can say I can solve the two in the same time. In this case, we will get wrong solutions. Okay, because of side effects of each pattern, they can change the graph. Okay. Okay. But the idea is it's kind of narrowing. So in the paper we call it GQ narrow. It's exactly the same. And in narrowing, there is one called needed narrowing. Okay, when all derivations should be needed, and it is the case here. It happens that the deterministic. Okay, but it's good to be deterministic.
This work was motivated by current work around languages, for example, this upcoming standard GQL.
Yeah.
And so, question is: have you discovered any flaws or ambiguities in this standard? So,
the standard has not been released yet. So I discussed with people, but I don't have the official papers. So they will work on property graphs, and from the papers we have, sometimes there's some difficulties to understand these property graphs. Some are clear, some are not. So I don't know what will be the final definition released.
A moving target.
Yeah, but the release is to be released very soon.
So that could be one motivation for carrying on this work.
Yeah. So we have projects with people working on Jekyll.
Yeah.
Yeah. And we're in charge to make some verification techniques. So we have to understand first what we are doing before verifying.
Okay, so let's thanks for speaking again. The next talk.
I don't know how to quit.
Well, it's okay if you open the windows again because it gets a bit warm in here, but I switched the light off, so I think the screens are good enough.
Okay, the next talk is formalization analysis of BPMN using graph transformation systems, and the paper was nominated as the best application paper. It will be given by Prost and Kräuter.
Yeah. Speaking of which, I like to present the award. So yes. So that is what do I have here? There's an envelope here with 3 copies. Okay. In case you want to distribute them, I don't know actually here. Yngve is here. You will get one. So I have another envelope, but I mean you can keep. You're traveling back together. Yeah. But anyway, there are two more envelopes here if you need them. And we don't have much of a prize, but if you want to have a celebratory drink at the bar tonight, it's still here. So there's a token that is good for 1 drink at the bar. Anything you can. And I've got one for the other best paper award as well. I was about to ask. So I can give you later. Right? Fine. Yeah.
Okay, so thank you everyone for this more practical talk. So a lot of great practical talk. I try to break a bit of flow and inject some from hopefully more practical stuff. This is joint work with my supervisors, Harald, König, Adrian, and Yngve Lamo, who is also here. And this work is basically, it's not adding anything theoretical. We're just using the powerful tools that have been developed by the graph transformation community to leverage them for this specific use case. And we're trying to formalize the analysis of BPMN using graph transformation systems. So let's look at the agenda first. So I'll give you an introduction. What is the motivation? Why is it useful? Why should we formalize this modeling language? And I'll give you some preliminary short primer of this modeling language and the theoretical background that it's basically using. Then I will talk about or introduce to you the BPMN semantics and how we formalize them using graph transformations, which is the main part. And then we'll show you the model checking, which results out of that using the graph transformation formalization and checking of certain properties, which is useful in practice. And then I will show you the tool demonstrate. So I've also developed a tool where you find all this implemented, and it's also accessible on GitHub. And then I will talk a bit about the data board. So there's not only one formalization of BPMN, there are multiple ones. I'm only one of them. And then we will, of course, go have a short conclusion, look at some future work, which is interesting. First of all, start with the introduction. Why is this useful? First of all, what is BPMN? BPMN is called the Business Process Modeling and Notation, and it's a widely used standard to design and to notate workflows in an organization or in spanning multiple organizations. You could think something like a company which is developing insurance products, and then there's a new customer who signs up on a website and says, okay, I want insurance. And then this will trigger a process which then models using this BPMN saying, okay, if someone opens a new insurance at our company, what should we do? Okay, save it in the database, send them some documents, and all these things, maybe we sign up for some service. So basically, what is exactly happening? What are the activities we're going to take if some certain business thing happens? There could be then later on that he has an insurance. He has an insurance claim, so maybe his bike gets stolen, then it will trigger another process, also modeled BPMN. And those processes, they can be different domains. I will show you a bit later. But the problem is with BPMN that it's only an informal description of its execution semantics. So you read the standards, it's basically described textually how these elements are supposed to be executed later on in your software. And there's, of course, because it's informal, there's always some wiggle room, some way to interpret it differently. And it has been implemented differently into different BPMN generally is very widespread in the businesses. They have a lot of these, they call them business process execution engines, where you just give them a business process and then they can run it on their software. And for each activity, you can provide in your favorite programming language, okay, I will run this piece of code, this piece of code. But you can still have this kind of model which shows you overall on a higher level what are the activities which are going to take. So you could ask, we're modeling this process, now you don't know anything about BPMN, so it might be hard to answer. You could always ask, does this process always terminate? Is there something wrong? Because obviously if it doesn't terminate, maybe some things are not getting executed, you're accumulating these running processes in your system, which could slow down the system, which would be an obvious mistake. So we will later on see if this process really terminates. This is something we can check, but we can check it only with the formalization. So without the formalization, it's of course difficult to check these behavioral properties. You could try to write some test cases, but there's always the question, do you cover really all cases that are possible? So there, in the formalization, you can really run some model checking. This is the more or less idea. So BPMN is very widespread in the industry, but they are using it without checking certain general properties like this termination, but you could also think about domain-specific ones saying, okay, if someone opens an insurance, then the activity saving the insurance in the database should be executed, so you could think about that. This is the introduction. And in my work here now, we propose a formal formalization based on graph transformation systems for the execution semantics of BPMN to check the behavioral properties. That's the main here. Look at some preliminaries. Let's look at BPMN first so you understand a bit more what it's about. So first of all, BPMN structure. So this is another example of BPMN. You have in general these so-called swim lanes, bigger boxes which contain elements which are modeling a process, and then you can have multiple of those in one BPMN model. And then these processes here, they can communicate, for example, via messaging. As you can see here, this process P2 is sending a message to the above. And we have these gateways, which are these diamonds, which are some decisions which are going to take. Do we follow the flow above or do we follow the flow below here? and then those cubes, so A, B here, those are the activities. So things happening. So activities could be something like we're saving something in a database, or even someone manually has to do something. So it's not be modeled in BPMN, and then it can be executed using the tool side. So this is an example. And then of course the structure is quite nice. There is a meta model which fits the structure. You can think of it as a type graph where you can type your model in. So this part is nicely done in BPMN. You can save it as an XML. It's quite nicely compatible. You can share it between tools. So this is not a problem, but we just have to know about it. So the structure is nicely defined. Everyone's working in the meta model, defined the specification, and it works quite nicely. And now coming to the semantics, when you really run these processes, it gets a bit more complicated. And this is what's important. So just one example here. We are starting this process, and now these tokens start moving through the diagram. Different activities are executed, and then the token is waiting on top and waiting for a message to come in. I will play it again. So usually with semantics, it's similar to Patron. It's described using these kind of tokens flowing through the diagram. Then you also have messages. Then you have instances of the different processes here. So we have an instance of the top process getting started. This is a very simple diagram. It can get bigger. There are a lot of elements, as you will see. And these semantics, which I will describe textually, we have implemented using graph information rules and generation of the graph. And the theoretical background which is used, which basically you guys have developed in the years behind, is basically that each state or each token distribution is represented as a typed attributed graph, typed in the BPMN meta model we've seen, and with attributes, since we'll see later here. We also have types and the element IDs recorded, but we also need attributes. So how we represent the state, we represent one instance of this tokens flowing through the diagram. Very simple. We say, okay, we have a process, we take a snapshot of the process at one time, and it has a set of tokens. So the tokens are distributed along the diagram, similar to PageNet, where you have tokens distributed in the state. And then we have a derived process state. So if the process is running, it has tokens somewhere. If there are no tokens, then it's terminated. This is used for graph transformation rules later. And then we have some messages which can also be here for this execution part. We only are interested in the things which are moving around the diagram. We're not interested in the structure which is fixed. This is the execution meta model I'm using. And then if you look at an example, so abstract syntax here in the middle, you can have an object diagram. But I will use, because it's a bit clearer and it's closer to what BPMN models are using, I will use this conflict syntax here on the right. And it's basically saying, okay, we have a process snapshot, so some process is running, circle on the top left. And then this process contains some tokens, so these tokens will have the same color. Now we have one token here sitting in the start event. And if you look at the abstract syntax, there's a connection, but it's abstracted away to the same color. You can say this token sitting at the start event together with the diagram. Nicely render it, and it will be more reasonable for people who know BPMN to talk about this abstract syntax than the complete syntax. And we're using the single push out approach with negative application conditions and quantified nested rules as it is implemented in groups. We use the group transformation tool, which is quite powerful here, and it also has these checking of properties, which we will see later on. And so far, SVO works well for all BPMN execution semantics, so there's no reason to look at other approaches. And this dangling edge removal is not really a problem. You can write or do it as you want. But as you can see, I'm only reusing what you guys have done in the way to work here in all these tools. Let's get to what I've really done. So this is the formalization of BPMN. First of all, to give you an overview, we start on the BPMN side. There's some kind of BPMN modeler in some kind of company. He's describing behind the BPMN model here on the top. And this BPMN model, as we've seen earlier, conforms to the BPMN meta model, which is the one I showed you earlier. And then you might find some behavioral properties to say, okay, I want to check if it terminates, I want to check if there are activities which are always executed or not executed. This is what the modeler is doing. So this is the BPMN world. Nothing graph transformation yet. Then we have the graph transformation world on the other side, where I'm specifically using the group tool, and I have the graph transformation system which goes into group. Group can understand the graph transformation system written in a certain way, and then using this graph transformation system and the properties on the left, and this arrow here, coming in, check that these properties are valid for our graph transformation system. So how these two worlds connect, so this is where my work comes in. This is already present. So what I've developed is we call it a higher order model transformation, which takes as an input the BPMN model, and it gives us an output a graph transformation system. And the graph transformation system is not just any graph transformation system, it's again typed in this execution type that I showed you earlier, right? The token distributed along these process snapshots. And I am the language engineer, or we are the language engineers, we are defining the higher order model transformation so that this transformation fits the BPMN specification. And we're doing this with so-called rule templates. I will show some examples later. And as you can see here, our BPMN model is somehow related to the BPMN meter model. But to keep things separated, I kind of duplicated it. The blue things in the diagram are the same information. But to keep them a bit apart, to keep them separated, I then improve it's a type graph, so it's done a bit differently, but it's exactly containing the same information you've seen earlier. But the idea with this approach is that you can change the left side and you can change the right side over time. So you can switch from BPMN to a different language, and you can use the same approach, or you can say, okay, graph transformation, I want to use something else. I want to use term rewriting, I want to use something else. But the general approach that should still be used. But here in this specific paper, I'm applying it to BPMN and graph transformation. So in summary, very easy, one sentence, generate a star graph and graph transformation is what you BPMN model. It's higher order transformation. Let's first look at the start graph generation. How does that work? So the idea is that we generate one process snapshot for each process in the BPMN model. And for each start event, we generate one token on each outgoing sequence flow. So let's look at an example where this very simple BPMN model, one process, one start event at least ground ones here, which are not coming on, with one outgoing sequence flow. And if we generate start graph, again, abstract and concrete syntax, choose which one you like more. I like the concrete syntax more. We have this one process snapshot, this is the one on the top left, and we have the one token on the outgoing sequence flow of the start event, which is the green circle with the one. So this is the start graph for this very simple model. If we have 3 processes in parallel, we generate basically one instance of each process and then run it. But of course, you could say, I want to analyze one process which is running 10 times. We have 10 instances, so you can provide your own start graph as well. If you'd like to analyze a certain iteration, right? Or you would start kind of in the middle of the process and you would use another start. But the general assumption is okay, we run the process from the start. Then we analyze what's happening. Let's look at the graph transformation rules, or again, the syntax. I'll give you one example of a graph transformation rule now. So in abstract syntax, again, we have the left-hand side and right-hand side. And here, token, there's one token, and change its element ID. So we're moving the token. You can see on the left-hand side, it's on this incoming sequence flow. And if you look at the concrete syntax again, we're basically moving one token in this rule, we're moving it from this incoming sequence flow with horizontal. We're moving it on top of the activity that started executing this way. And this is basically how I will show you now. From following on, I will also show you the concrete syntax on that. But you can see the relation. Otherwise, check it in the paper or ask me about it. So I showed you one example rule, but how are the rules generated? In my approach, I generate a set of rules for a specific BPMN model. There are other approaches which basically define a fixed set of BPMN rules, which can cover all models. But this approach is different. So we generate one specific set of rules for each specific BPMN model. And the idea is that each BPMN flow node, so each node in this graph, which has some kind of execution attached to it, is transformed to one or more graph transformation rules. If it's a simple node with simple execute semantics, we just need one rule to represent it. More complex, we might need more rules. And now, to talk everyone, this is BPMN. This is everything I supported BPMN. There's even more stuff going on in BPMN. And the green, you can probably not see, but there's some green underlined. This is described in the paper. But for this presentation, I will stick to some simple examples. I will stick to the activity. I will show you how the generation of rules works for activities. I will show you how it works for end events here at the bottom. And I will show you how it works for these two gateways. But all these other ones are also implemented, and they cover not everything in BPMN. You can see later there's little features which are uncovered in BPMN, which wouldn't put still in the future. So let's start with the activity. You've kind of seen already a sneak peek on the previous slide. So the BPMN flow will be on the left, and then this rule generation template is kind of the idea how we generate rules in the general case on the right. So we have an activity, and in general, if you look at activities, they can have I incoming sequence flows, and then they can have J outgoing sequence flows. They are not simple, and they have one incoming and outgoing, they have kind of multiple combination. And here with this, we generate one rule for each incoming sequence flow. This is what the formula is here. So if there are 10 incoming sequence flows, we generate 10 rules to represent the spark infinity. And then for the specific sequence flow we use, we just move the token as we see before from the incoming sequence flow to the activity. This is encoding the starting of an activity. And then to encode the termination of an activity, we only need one rule. It doesn't matter how many flows there are. We take the rule from the activity, we take token from the activity, we delete it, but we add one token on the output. This is the idea here. So this is how you represent activity. And then depending on the complete activity, if you have one incoming sequence, so one outgoing sequence, you'll get 2 rules, and otherwise you might get more rules from complex scenarios. But usually it's the best practice, maybe this is your question, usually it's the best practice with one incoming sequence flow and one outgoing sequence.
So the question is why would you do that with the generic rule, but you have to kind of make one rule that just does it in all those cases.
Yeah, you could probably do that, right? So the thing is that if you've seen earlier in my execution model, I've thrown away all the different structure. I only have the tokens. Tokens are moving around. So I would need to change it a bit so I still have the structure. I still can represent it. So far we've done it this way, a lot of rules. I'm not sure if this is the best way to do it. Maybe it's not.
But it's interesting to understand.
Yeah, this is one of
your rationale behind one or the other option. But I know both is possible.
Yeah,
but certainly.
So here the idea is that the complexity is in the model transformation, because they were generating a lot of rules. If you move it into the graph transformation, then make it a little more complex, right? So it's a trade-off which I have not explored, which is the best option. Let's go on with the end event. The end event is very simple. As I said, you can have again any amount of incoming sequence flow. The token is the token of the incoming sequence flow, and then our process terminates when all tokens are deleted. So there's nothing done anymore. So those are the first two. And here again, you generate one rule for because there can be multiple combinations. There can be tokens coming in on conditions. But usually, again, the best practice is the demand to look at practice they only once incoming sequence flow. But the specification doesn't forbid situations like this. But it's not the best practice. It's true. Yeah. And then the last one I wanted to show to you is the gateway. So the parallel gateway. It's basically synchronizing all the incoming flows and paralleling all the outgoing flows. I can move on the left side. Neglected people on the left side a bit. Here we have one token on each incoming sequence flow, and we generate one rule again, and we expect one token on each incoming sequence flow. We delete it, and we have one token on each outgoing sequence flow. It's very easy, and it's basically saying if there's 3 things happening in parallel, they will synchronize by our gateway, and if there are more flows going out, we'll run multiple things in parallel again. So this gateway is used as a synchronizer and a parallelization at the same time. But usually in practice, you either synchronize or you either parallelize. Usually don't mix it, but our rule can have both situations, right? And then the exclusive gateway, again, now we get a lot of rules. Because the exclusive gateway basically says we can have as many incoming sequence flows, outgoing sequence flows as we want, generally. And the idea is we pick one incoming sequence flow and we pick one outgoing sequence flow and we move the token. So now we get the Cartesian product of the incoming and outgoing sequence flows, we get all the combinations, and for each combination we generate one rule saying, okay, if there's a sequence flow incoming on this specific, if there's a token incoming on this specific sequence flow, we move it to the specific outgoing sequence flow. Because this is like a decision, we either want to follow this path, or this path. Then we need to pick a specific path to follow. But by having all the rules, we will explore in our model checking, we'll explore all the different paths through the model. So these are only as you've seen earlier, these are only the very easy BPMN semantics which are implemented. If you get to events, there's much more stuff happening, and that's when we need the nested application conditions. That's when we need non-application conditions, because then it gets more involved. So these ones are rather easy, but then if you get into the thick of it, it's getting harder. Okay, let's talk a bit about the model checking part. So now we have our graph transformation system. Now we can run it, so hopefully we can do some model checking. So how does this work? So here we are reusing basically the work done in Groove. So we have our BPMN, our properties coming into Groove. We have a Groove, of course, and we have the graph transformation system generated by our higher order transformation. and then we can run groove in the background. You will see later on in the tool to check for specific properties. And the first kind of properties we want to check are these like more general properties. And these general properties, they come from Petronets. They've adapted them a bit from Petronets. And the first one is this safeness property, which says, okay, are there more than 2 tokens on a sequence flow at any given point in time? That would be kind of fishy. This option to complete is this kind of termination I was talking earlier. Can my process always terminate, or is there a combination of gateways I am taking which leads to our process instance not terminating? So this is like a general property you can check for each of your model. And then are there dead activities, which is similar to dead code, right? You want to eliminate those. We can also check for those. And these are coming from the literature, the work on BPMN. And with our approach, we could check all these properties. You will see later in the tool. And for safeness and for option to complete, we're using at the end CTL properties, which Groove can run then in the background. And for no dead activities, we need to check that each activity gets executed in any flow through the graph transformation systems. We basically analyze the state space generated by Groove and check, because the transitions are the graph transformation rule applications. We check that there is a transition matching each activity. So then we know, okay, these activities are getting executed. And then there are like these kind of custom properties. If you have a specific domain, as I said, like the insurance domain, we create an insurance, then we want maybe the activity to save the insurance to also be executed later. These are kind of custom properties for maybe your specific domain. Those custom properties encode essentially like domain-specific requirements, nothing general, something specific for your case. And for those, you need to define, first of all, the atomic proposition, so kind of the state you want to reach or the state you don't want to reach, for example. And you can use the concrete syntax. That's the idea. It's not implemented yet in the tool. You can use the concrete syntax saying, hey, this specific state where we have 2 process snapshots, which have a token at this activity, this maybe we don't want to reach. And you can check this because in our domain, maybe this needs 2 people are working on the same task at the same time. It's a manual task. They will get in conflict. So we don't want this to happen. You can, depending on the domain, you can come up with examples. And then you need to write a temporal property at the moment, for example, CTL, to check this property, which is not so nice for BPMN modeler. So there's still some work involved to maybe make this a bit easier. And then this can be checked again using Groove tool in the backend. So let's jump to the tool demonstration. I have to go here again. Sorry. So let's look at the tool. Should see it now. So yeah, the tool it's a web-based tool, so you can run it. But there's a link to something online. You can just use it. So the first thing is you model some kind of BPMN on the top. So here we're using something before, but we will upload the model you've seen earlier in the introduction. So we have this demonstration model, right? I was wondering if it terminates or doesn't terminate. So now I've uploaded it here. And the first thing you do is you just want to run the model transformation. You can click on this button, and this will generate now a Groove graph transformation system. You can download it, open it, Groove, play with it. And usually these BPMN modelers, they don't want to see what's going on in the background. They just want to check their model. So you can select here these different properties. So here we are selecting option to complete. We can check the property. Now this is running on my laptop. So it's reasonably fast, but not super fast. And here you can see, oh, this process can get stuck, so it might not terminate. And here the problem is, if you look at the process, we have mixed kind of 2 types of gateways. We have here the exclusive gateway. There will be a token coming in. It will choose one of the flows, maybe this one, go down here. And now we have a parallel gateway, which expects 2 tokens coming in to execute. So here someone has mixed up the gateways. Could happen quite fast. They look very similar. This would be something which is detected. And then we can also check for dead activities. And as you can see, since it gets stuck at this parallel gateway, our tool will now tell us that there is a dead activity. And this dead activity is now highlighted in the tool. So this activity C can never be executed because the process gets stuck for that. And then you can also run custom CTL properties here, as I said earlier. So this is a tool demonstration. Regarding related work, I'm not the first guy from the development this. They are sometimes using graph transformation, sometimes using other means. And I have compared my approach to other approaches regarding the features BPMN elements we covered. And there's a big table in the paper. The most important takeaways are there are some features only I can support currently, at least regarding the related work I know. There are some remaining things we could take from other people, how they implement them, especially there's Van Work who also use graph transformation to implement 2 features I have not implemented yet. So it's a nice inspiration. You get a very good idea of how these things could be implemented. So there's still some work to do. But more regarding the practical application, like features we have covered now, they are very close to what people execute in practice. They're very close to the features people use in practice. So we're only missing some small features regarding the process they're using in practice, because there are a lot of elements in BPMN where people say, stay away from those, they're too complicated, don't use them. So they are bad practice using those, they're not really implemented in a lot of these BPMN engines executing these processes. And the idea is we get the same coverage and tools in practice, and then we can check those processes, right? That's the main idea. And then for conclusion and future work, just to summarize, we have this higher order based approach to transform BPMN models to graph transformation systems. And it's quite general, so you could say, okay, I'm not transforming BPMN, I could try something else. Or I'm transforming not to graph transformation systems or to a different tool in graph transformation system, quite a lot of different things you can change. Our BPMN formalization is quite comprehensive. Looking at the table, you have to trust me, I just skipped over it. And model checking is supported, right? So we have like nice graph transformation tools which we can use in the background. We have a tool implementation which is web-based. There's still work to do, but it can check some properties. And for future work, of course, we would like to extend the formalization to cover at least what they do in practice. We need to evaluate our approach on models coming from practice and looking at the scalability, those kind of things. The never-ending question. And then we want to extend our implementation to make it usable, maybe integrate it with the practice in a regulated model. So the things. That concludes my presentation.
But one quick follow-up, Mark. Like the question, so this is like population participation. You're essentially compiling BPMN tool system, which can be quicker depending on whether this actually benefits mostly the matching phase of the rules.
Yeah.
So, any comments on that?
I hope it makes the matching faster because we have smaller rules, right? We have a lot of rules, but they are quite small. And also the graphs, since I don't have the structure of the BPMN and the graphs are quite small.
Yeah.
The graphs are just the post snapshot links for we're matching those.
Maybe I'll ask you later on how the matching is actually done, because that's quite not.
Yeah, I'm not familiar how that is done, so.
And once further questions, what would be needed to actually turn this into a BPMN engine?
What do you mean by engine, like executing BPMN?
Yeah, so you said there are these tools that actually use BPMN.
So to turn it, so they have activities which are associated with code, which is getting executed. They have some infrastructure for these messages getting sent. They have some infrastructure for the history of BPMN. So they have long-running processes running for days, weeks. So they have a database there. The power goes out, you know which processes are running, right? They have some infrastructure for manual tasks. If there are manual tasks, people can log in some website for the manual tasks. There's still a lot of things going on around. But you could say, okay, the execution, maybe the execution part, we could say, we would check it, or we would see it matches what we're doing.
But process control.
Yeah, you could say the process control.
Workflow engine, but not the integration of the workflow engine
with all the rest.
Basic activities.
Yeah. I see it as more like use it as design tests. We try to catch bugs as early as possible, right? That's why
You have used graphic writing essentially to shift the token
yes.
activity. So graphic writing for execution.
Yes.
There are some applications where the nets are changing at runtime. For example, the case of evolution dynamics. You are implementing a software system. After the architecture, you know how many modules you have to insert. You know how to do that. So you need structural changes together with execution. Did you think about that?
No, I didn't think about it. So the thing with BPMN is that you don't have this feature. You cannot change the models. You cannot change the process models on the fly. What they do in practice is they say, okay, something has changed. Maybe a new requirement comes in. We will change the approach. We'll make a new version, right? And this version will get deployed to production. And then, but then you have a new model and the old model is out of the picture, and then you can run the checking on the new model again. But it's not like we're running things and then we're changing and then we keep running. And all the old instances will run on the old model and all the new instances will run on the new model. But this would be something very interesting, right? You have some instances still running on the old model and you would like to migrate them to the new model. So this is something I haven't thought about. I think it would be quite complex, but it could also be very useful for the event people.
It will give you some picture.
I'm looking forward to that.
Okay, very quick one. You mentioned those gateways, particularly if you've got, say, NH is coming in and going out, you know, with end-to-end. Yeah. But you could, I think, rewrite that as an end-to-one gateway followed by a one-to-end gateway, and then you've only got about 2 airlines. Is there scope for benefiting from that kind of sort of pre-process?
So then you would have booked at gateways, right? This way, which is so because you say, okay, put it on the gateway.
I'll insert trivial tasks between them.
Yeah. So generally, so I thought about this and use some of the rules, right? But I try to stay true to how it's written. The specification, they say tokens should not be on gateways at any point in time. But of course, right, for the checking, you could say, okay, we're generating it, but the user never sees it. But maybe it's like an optimization down the road.
But you could just insert the do not task between the two gateways.
Yeah. But then we should definitely analyze how this affects like the state space and analyze it. But I was of the opinion that like premature optimization, like we can call evil as called normal. So
that
we keep it for later. We keep it for later, and if we see that for the loop activity, some people say you can just model it in gateways, just have like a model the loops manually using the gateway, right, and go around. But this is not the loop activity, but you can, it's a workaround, right? And I'm not sure on top of that, but I think that some of the programs say don't support it, you have to model it, you can model it by your own. So this would be something I still have to look at. Yeah, so far I said, okay, there's a workaround.
Okay.